Good evening, everybody. It's really good to see you all here this evening. This evening is a very important event. First of all, it is the inaugural lecture for the Kingman Speaker Series. This is going to be an annual event, and we will hear a little bit more about that in a moment. But make sure that you mark this on your calendar, come this year, and keep coming. It's also very important because we have an outstanding speaker for you tonight. David Reitze, and he, I know, will be a fascinating, and even though it's later in the evening, no one's going to fall asleep. So thank you for coming. Many of you are from this community. I think some have traveled from a bit further, so a particular welcome to you if you are an out-of-town guest. And I'm going to pass over now to Dr. Mattingly. He's going to talk a little bit more about the series and the beginning of this series. So Dr. Mattingly, and thank you for coming.
Thank you, Dr. Luxton, who is the president of our university. You know, it's quite a privilege to live in a community that is close to a university, don't you think? We get some really neat speakers, and we've had some really nice ones here at Andrews through the years on a variety of different themes, whether it be archaeology, whether it be history, whether it be theology. But you know, there's been one area that we haven't had so many of these kind of events. And this made a difference to the Kingmans. Robert and Lillis Kingman visited me about a year ago when I was Dean of the College of Arts and Sciences with a proposal. And their proposal was, we'd like to endow a speaker series that focuses on the STEM world. Well, you all know what STEM is, right? It's not stem cells. Somebody talking to me earlier thought it was stem cells. I said, no, STEM is science, technology, engineering, and mathematics. And the Kingmans would like to see a speaker series in which we can bring in significant people in the world of science, technology, engineering, and math. And so they have endowed this, they offered to endow this kind of a series. So I took it to the president, took it to the officers of the university, and they accepted the proposal with excitement. And so tonight, we are at the inaugural event, which the Kingmans have sponsored. The endowment kicks in next year, but this year they have sponsored this event, and we were able, by hook and by crook, and by people knowing Dr. Reitze, that we could get a speaker in of this caliber. And so thank you. Margarita is going to be presenting Lillis a thank you for this evening, and we want to thank the Kingmans for their foresight and for their generosity in helping us have an evening of this quality. Thank you.
So it is my privilege to welcome Dr. David Reitze. I've known him now for many, many years. We worked in the same femtosecond spectroscopy laboratory at the University of Texas. He got his PhD just 2 years before I did. We both went our separate ways, and neither of us ended up in femtosecond spectroscopy. And both of us ended up in administration, believe it or not. He is now the director of the LIGO project, which won the Nobel Prize for physics 2 years ago. Now, he didn't win the Nobel Prize. Neither did about 1,000 of his colleagues also in LIGO, because only 3 people won the Nobel Prize. But it's my pleasure to welcome Dr. David Reitze.
Thank you, Gary. Thank you so much. First, let me say I'm really delighted to be here, and especially at the inaugural lecture, the Kingman lecture. So thank you so much for inviting me. So what I want to talk about tonight is a revolution in the way we do astronomy. And I don't use the word revolution lightly, and I don't mean it in the sense of we're overthrowing governments or things like that. I mean in the sense that if you look up revolution in a dictionary, that's actually the first definition you get, overthrowing existing government structures. But the second definition that you get is basically dramatic paradigm shifts in the way we understand something or study something. And that's what I mean in this particular case. So I'm going to tell you in about 15 minutes or so the story of detections of gravitational waves that have happened over the past 4 years. But I'm going to start by going way, way back, actually, to the time of Sir Isaac Newton. All right? And we have to talk about this concept, this physical reality that we all live with. It's called gravity. It's why we're all sticking to the Earth. Gravity's been studied historically for thousands of years, but it was Sir Isaac Newton who first began to really understand what it is and was able to write down mathematical formalisms that could explain how objects behave and how gravity attracts objects. So let's start with the sun. If I have a big massive object called the sun, I'm just going to put it there, and then I'm going to put the Earth there. And we all know that the Earth orbits around the sun, other planets orbit around the sun. Sir Isaac Newton explained this in the following way. He said that the attractive force, masses are attractive, is proportional to the mass, that quantity m there is basically the mass, the amount of matter in the sun, and it's proportional to the amount of matter in the Earth. He also determined, and actually there were experiments that had to be done here, that it's proportional to the inverse of the distance between those two objects, the sun and the Earth over here. And that proportionality constant is very important. It became known as Newton's gravitational constant. It's actually a pretty tiny number. Now, there's a problem with Newton's theory that even Newton recognized, but didn't have the knowledge or mathematical tools at the time, or actually a lot of the physics that was needed to understand. The problem is that how does the Earth know that the sun is there, and how does the sun know that the Earth is there? It's like this magical force that's attracting one object to the other. And the answer is Einstein. Einstein, who was a brilliant physicist on many, many levels, and of course I think he's probably the most famous physicist that ever lived, it basically came along and said, it's not that the sun knows the Earth's there, the Earth knows the sun is there, it's that they communicate through something called geometry. And so this is basically a pictorial version of the theory of general relativity. That green curve, or that green mesh that you see at the bottom is sort of an artist's conception, if you will, of space and time. And the quantities of space and time and matter and energy get mixed up in general relativity, and I mean mixed up, and literally they're equated to one another. So how does it work sort of physically from your intuitive standpoint? Well, you put a mass, any kind of a mass, in space, and the space changes. It actually changes its geometry. It warps. All right? And you put another mass in the space, and the other mass also warps. The reason in this theory why the sun and the Earth are attracted, and why the Earth orbits around the sun, of course the sun is much more massive in this case, is that the geometry of space sort of is telling the Earth that it needs to actually move in that curved orbit around the sun. And you can kind of get a hint, even though this isn't a perfect analogy, you can kind of get a hint by looking at that picture there, that there's a bowl around the sun, and the Earth, all right, is following the natural geometry that it follows. And more importantly, it also explains how the force of gravity is communicated. And the way the force of gravity is communicated is through that space-time right there. So if the sun were to magically disappear, all right, the curvature of space would relax back to its sort of, we call it flat geometry, and it would have to, that information, that space would have to propagate out. And about 8 minutes later, which is the light travel time between the sun and the Earth, the Earth would go, oh, there's no more sun, and would just fly off into infinity in a straight line. All right, the challenge with this whole trying to do this experimentally. It's a beautiful mathematical theory. It was validated by solar eclipse experiments in the early 20s by Sir Arthur Eddington, where he showed that even light does not travel in a straight line, that light has to travel in the geometry that governs it as it's going through space, and that light gets bent as it goes around the sun. So this is a remarkable discovery. It immediately put Einstein on the front pages of all the major newspapers in the world as the preeminent physicist of his day. And their relativity sat as an experimental science for a long time, because the problem is that number that comes between after the equal sign. It's 10 to the minus 43. So it's 0.43 zeros and a 1, roughly. All right, which tells you that you need a huge amount of matter and energy, a huge amount of stuff to even just a little bit bend space. So space, in this sort of analogy that I'm using, is very stiff. All right. Now, that might not be so intuitive to understand, but the other way of thinking about it is that gravity is actually a very, very weak force. And you might not believe me if you're climbing up a ladder or climbing up stairs or something like that, but the fact that a person who weighs roughly 50, 60, 70 kilograms, all right, can walk up and fight the gravitational attraction of the Earth, which I don't know the exact number, but it's trillions and trillions and trillions and tens of trillions of kilograms, tells you how weak this force is. And that's the challenge that you faced in doing any experiments in gravity. So there's another prediction of Einstein's theory that's very important, not only for what I'm going to talk about, but also just in general, and that's the formation of black holes. If I go back to this picture, if I put enough mass and I put it in a small enough volume of space, the curvature is going to get bigger and larger and larger and larger. And eventually, the curvature will get so large that something forms called a black hole. All right, and these black holes exist. Actually, they're ubiquitous in the universe. They were proposed actually originally in Einstein's theory in the 20s and 30s. They weren't believed to be existent for a while, and now astronomers, or in the past 20 years, 30 years, astronomers have discovered them. However, they're very, very unique objects because they're very compact. And there are places where space, we don't know what happens to space-time. There's something called an event horizon. And there's this wonderful picture that was taken. This is of galaxy M87. This is a picture that was taken of the center of that galaxy. It's called by the Event Horizon Telescope. This is a radio telescope, and they made an image. And that black spot that you see in the center is not actually the black hole itself. It's the shadow image of a black hole. And what you're seeing are basically the radio waves coming around it and used to reconstruct the image. This black hole is quite special. It's the first black hole that's ever been imaged. It's also a supermassive black hole that roughly its mass is about 6 million solar masses. And it turns out that at the center of every galaxy, you have these supermassive black holes. All right, so the black holes are quite interesting for us, and as you'll see later in the lecture, we're going to come back, and where we look at these black holes is we look at them in pairs. Another thing that the theory of relativity, general relativity does, is it predicts the existence of waves, these things called gravitational waves. So what is a gravitational wave? All right, it's, as the name implies, it's waves of gravity. So I'm going to play a little movie here. Let me set the movie up. In this case, those two black dots or small spheres that you see are an artist's conception of two black holes. And as those two black holes orbit around one another, well, you'll see what's going to happen. Let's watch the movie. All right, you see they're orbiting around one another. Space is rippling as it goes out. You see that they're getting closer together. They're actually spinning a little bit faster and a little bit faster, and eventually they're going to collide and produce a big black hole and a burst of gravitational waves. So this is a fundamental prediction of the theory of relativity. It was predicted in 1916, so over 100 years ago. Now, it's quite interesting that Einstein himself, after he wrote the paper predicting that gravitational waves existed, he basically this is a paper that was published in 1918, has a throw-off comment, all right? And this is actually a Google snapshot, or basically I got this from Google. This is the actual paper, all right? And that quantity A in that equation, this is the only equation I think I show you in the whole thing. And you don't have to, the details don't matter, but that quantity A is related to the amount of gravitational radiation or waves that are produced when these two objects or any object is emitting gravitational waves. And Google Translate is wonderful, so you can actually translate that underlying part there. And it said that A must have a virtually vanishing value in all imaginable cases. So what is this telling you? Well, this is Albert Einstein saying, all right, look, they may exist, but don't look for them because there's no way you'll ever find them. They're too feeble, they're too weak. And it comes back to the nature of the unique nature of gravity as a force. All right, so that would be discouraging to you if you were an experimentalist trying to build a detector to build gravitational waves. Einstein himself is saying, don't bother. Interestingly, about 15 years after this paper was published, Einstein came to the conclusion, after doing a little more work, that gravitational waves don't even exist, that they're a mathematical artifact of his theory. And he actually was going to publish a paper to this effect, and he sent it to a famous journal in the physics world at the time, the Physical Review. Many of you who are scientists know that we have something called peer review. And so the paper that Einstein submitted was sent out for peer review, and the person who peer reviewed it basically wrote back and said Einstein was wrong. In fact, they do exist, and he just made a slight mistake in his, both in the mathematics but also in the interpretation. And so Einstein got this nice letter from the editor of a Physical Review saying, "Dear Dr. Einstein, thank you for submitting your paper. We've reviewed your paper and cannot publish it because it has an error." Einstein wrote back to the editor of Physical Review saying, "Dear Doctor," I believe his name was Robertson, he said, "Thank you for your letter. I did not ask you to review my paper. I asked you to publish it." Right? But since you will not, I'm taking my paper to another journal. And in fact, he did try and do that. He later admitted that he was wrong. He was corrected and that he believed in gravitational waves. But it doesn't get around the problem of they're tiny. And so Einstein himself thought, why, you can't do this experiment, so why bother? And the answer has to wait some time for technology. But basically, everything we know about the universe, we know in the large-scale universe, we know from a couple of fundamental tools. And I would say there are really three messengers, three things that tell us information about the universe. The first is light, or photons. And we build these wonderful, huge telescopes. This is a picture of the Keck telescope on Mauna Kea that makes these wonderful images. We can analyze the character of the light, the color of the light, and that tells us a lot. We also have neutrinos. All right, neutrinos are kind of exotic particles, although they've been known for almost 100 years now. And they actually carry a lot of information about violent astrophysical events in the universe. And then we have particle colliders. This is a picture of the Large Hadron Collider. And each of these types of tools or types of telescopes tells us, gives us valuable information about the nature of the universe. Gravitational waves are fundamentally different, all right? They're unique in the information that they carry. So telescopes, for example, you might ask yourself, what do I learn when I look through a telescope? The answer is what you're learning about is the motion of electrical charges and basically magnetic fields and things like that. Electromagnetic radiation, which is what we call light or photons, is produced as charges accelerate and move around. Right? Gravitational waves are fundamentally different. They're produced when mass moves around, when masses accelerate, as I showed in that video a little bit earlier. So they're a new way to look at the universe. They actually have some unique properties. They go through matter almost like it's not there. So there's no absorption of gravitational waves. So you right now are being bathed by low-frequency gravitational waves from the Earth moving around the sun, more importantly from the moon moving around the Earth. As I wave my hand here, I am generating gravitational waves. You don't feel anything. The reason has to do, again, with the fact that gravity is so small. So they also are a different kind of messenger, and they carry information about the most energetic, violent events in the universe. So the reason we study gravitational waves is not so much to prove that Einstein's theory of general relativity was right by verifying that they exist, but it's to sort of study a new regime in the universe. So, all right, so now let me come to how we actually do it. So what are they? What are gravitational waves really? I showed that nice cartoon with this, sort of ripple of, sheets going out and things like that. Physically, what they are, when you actually start to study them, and they're a quantity called strain, and if there are engineers or physics people in the audience, you know what a strain is. It's a change in length per unit length. So if I take, for example, a piece of steel, and I compress the piece, if I put a force on a piece of steel, all right, the steel will actually compress ever so slightly, minuscule amounts, because basically the nuclear and the electromagnetic forces really in the steel push back. That's essentially the same thing that's happening with gravitational waves, is there a strain. So they're a change in length and unit length. So this cartoon shows you what would be happening if a gravitational wave were coming out of the screen. So they come in two flavors, or two polarizations, and that just shows that. So you see in one dimension, all right, the coordinate system. You can think of this as a coordinate system that's placed in space. The coordinate system is stretching, while at the same time the other dimension, the orthogonal perpendicular dimension, is compressing, and this cycle continues. All right. Now, I said that gravity is a really weak force, so we might expect that this also might be a very feeble effect. But let me just motivate how you start to think about making a detector that's capable of measuring this. And you realize that if you pick an arbitrary point in space where there's two black lines cross, and I make a measurement there, all right, you see that I'll do it again. You can see that, as that stretching happens, the arrow moves a little bit. But if I wait and go a lot further and move the arrow out there, there's a lot more. So the way you want to detect a gravitational wave is you want to basically measure it over as long a baseline as possible. So if you're an experimentalist, you're trying to measure the tiniest displacement possible, and you're trying to measure it over the broadest baseline possible. All right. And I wish I could say that that's all to measuring gravitational waves. If that were true, it would have been done many years ago. The challenge, again, is now one of size. So we're going to do an experiment. And this is why Einstein was actually right when he made that statement in his paper. All right, this is an image I got of probably a science fiction movie in the 50s. This is a mad scientist here. This mad scientist is going to try and make a gravitational wave generator. The way he's going to do that is he's going to take two massive spheres, let's make them iron. He's going to make each of them 1,000 kilograms. He's going to separate them by a few meters here. And I want you to pay close attention to this gentleman over here. And he's the smartest person in the room in this experiment, because what this guy is going to do is he's going to spin it around 100 times a second, or even 1,000 times a second. Now, don't go and try this at home. If you calculate, and you can calculate, what the magnitude, the amplitude of that gravitational wave is, it's a small number. It's 10 to the minus 35. All right. So that means that the distance that's changing, all right, if you're a distance away, in this case we're about a few hundred meters away, is 10 to the minus 35. So that's an impossible number to measure, and you would just say to yourself, okay, there's no point in even trying to do an experiment because we can't do it. But it turns out nature is very kind in this regard, and it gives us a system that behaves very much like this. These are two artist drawings of two neutron stars. What are neutron stars? They're formed when stars explode, if the stars have the right mass, and they're very compact, dense objects. They're about 25 kilometers in diameter, and they have a mass that's about 1.5. It's 1.4 is the canonical mass of these. And they also, you find a lot of them in pairs. We know that stars and neutron stars pair up. So if you do that same calculation, so this is exactly the same experiment, but nature is doing it for you, you come up with a number that's still awfully dauntingly small. all right? But it's 10 to the minus 21. But it's not impossible. It's not impossible to measure. But this sets the scale for the kind of detectors that you have to make to be able to detect gravitational waves. And in this case, the gravitational waves fall off. Remember I told you that gravity falls as 1 over the distance squared. The amplitude of the gravitational wave falls off as 1 over the distance. And that's actually a very important point in all of this. So, all right, so I've sort of set the stage for you. And now I want to tell you about the Laser Interferometer Gravitational Wave Observatory, which is the detectors that we use to measure these wonderful events. And you will see I put a logo of the National Science Foundation, the U.S. National Science Foundation on this. That's because they have graciously supported this research for over 40 years. So this is our detector, and it's a pretty impressive detector as things go. Just to put a sense of scale, that green dot that I'm projecting, that's a car. All right, so you have this thing that's shaped like an L. And these are arms, and they're about 4 kilometers long. And we have not only one of them, this one's in Louisiana, we also have one on the other side of the country in Hanford, Washington. It's essentially a clone of the one you saw in Louisiana. However, it's about 3,000 kilometers away. All right, so we have not one, but we have 2 detectors. As I go through the presentation, you'll get a sense later on for why we want more of these detectors. Okay, so I said H is delta L over L. So we're trying to measure this quantity H. This is the amplitude, again, of the gravitational wave. All right, so L in this case is 4 kilometers. Okay, that's good. We made L pretty large. All right, how big does H need to be? Well, let me tell you about interferometry first. All right, so the way this actually works is that we start with a laser, so that cylindrical object is a laser. The thing that sort of looks like a thin line, you'll see that it's not, is something called a beam splitter. It takes the laser, it splits it into 2 equal beams. One of those beams it reflects and sends perpendicular to the original laser beam. The other beam goes through and transmits. The light comes back and recombines. And let me, again, show you a nice sort of movie about how these interferometers work. All right, so you'll see we're going to start with the laser beam. It's a ribbon in our case, and we're going to color code the wavelengths. So the laser light is very pure. It has wavelengths. And wavelengths are a perfect ruler. So the light comes back. It reflects off the light, comes back. And if we configure the interferometer just right, all of the light comes back towards the laser. None of it goes towards that end there. You see destructive interference, so that's over there. But as a gravitational wave passes, one arm gets a little bit longer. You saw that from the gravitational waves before. The other arm gets a little bit shorter. And what happens is the interference pattern changes. So basically what's going on here is you have this passing gravitational wave that's hitting this interferometer. It's changing the length of one arm relative to the other arm. One arm is getting longer, the other arm is getting shorter. That changes when the light comes back. And what we're actually measuring here, we're not measuring the wavelength of the light because that's actually changing too. It's being stretched and compressed. We're actually measuring the time of flight, how long it takes for the light to go up and back. And it turns out it gets a little bit longer in one arm that stretches, a little bit shorter in the other arm that compresses. And basically this transduces the interferometer starts, the arms start wiggling, and we start basically producing light. So what we're doing, and this is really a remarkable thing, is that this interferometer is, in physics we'd call it a transducer. It's taking the ripples of space-time that are produced by some object generating gravitational waves and turning it into light that gets detected by a photodetector. This is the same kind of photodetector that you have, for example, the photodetector, I don't have my iPhone with me, but if I did, the detector in my iPhone is much more sophisticated than that photodetector there. It's just an object. And it records the light modulation due to the passing gravitational wave. The light is going, it's getting brighter, it's getting darker as the gravitational wave passes, and it keeps going on and on and on. And that turns into current, all right? So basically, we're taking these ripples in space-time and turning them into current. And actually, our detector is sensitive to a very specific band, a frequency band. It happens to be sensitive from 20 hertz to about 2 or 3, 4 kilohertz. And some of you in the audience those numbers might be familiar to you. That happens to be the audio band. That's the band where our ears are actually sensitive to sound. So this detector, all right, is basically taking gravitational waves and we'll turn them into sound, and you'll see that in a little bit there. Okay, so I exaggerated. Let's go back to that movie. All right, I exaggerated the shifting of the wavelengths relative to one another by about a factor of 1 trillion, just to show you the effect. All right. In fact, the distance that's changing and the shift in the wavelengths that we're seeing, all right, is measured on a subnuclear scale. So this is a artist's conception of an atom. This is a graphic artist we work with at Caltech who's really a brilliant artist. So that streak of red there is an electron zooming around a proton. So this is a hydrogen atom. Right? The dimension of that atom, just for scale, is 1 angstrom, on the order of 1 angstrom. And that, in units that you might understand, is sort of a billionth of a little bit. It's actually 1/10 billionth of a yard, or 1/10 billionth of a meter. So it's tiny, tiny, tiny. Can't see atoms. All right. So let's see what happens. So we're going to zoom in. All right, and there's a grid for scale. Now we're zooming in. We're well into the atom. We're now looking at the proton at the center of the atom. That's 10 to the minus 15. And this is the amount of motion that our interferometers can detect. So it can detect about 1/1000th, a change in motion, delta L, about 1/1000th the diameter of a proton. So that's very, very sensitive. And we go to a great deal of calculations, of prototyping, of testing, to be able to make an instrument that's sensitive. And the details of the technology are fascinating, but also take a long time to explain. So I'm just going to walk you pictorially through some of how we do this. So this is a picture of the inside of the corner station. So that's the station that sits on the L of the LIGO detector. You can see it's quite busy and quite crowded, so that little cartoon I showed you is really just that. In this picture, the laser sits down here, the beam splitter sits right here, the end mirrors you can't see, they're 4 kilometers away from here, and all of this equipment is basically a giant vacuum system. So we actually have one of the world's largest vacuum systems to be able to do this experiment, because we don't want the light to be deflected by atmospheric perturbations. All right, so let's zoom in. This is the laser. All right, it's one of the world's most stable, I believe it is the world's most stable laser in terms of something called wavelength stability and amplitude stability. Here is a picture of our actively controlled seismic isolation. When you make an interferometer, the interferometer is subject to a lot of vibrations. We're trying to make very, very sensitive measurements. One of the biggest vibrations that we have is the Earth itself. So you don't feel it as you're walking around, but the Earth below you is actually moving, and it turns out it's moving with an amplitude of about 1 micron. That's 1/millionth of a meter. All right? We're trying to detect things that are about 10 to the minus 18 meters. So how do we isolate those things? And the answer is that we use basically something that you have in your car. If you drive a high-end luxury car, it has active stabilization. So if you're driving over a bumpy road, the tires are going like this, up and down, whereas the ride feels very smooth. So we do that same thing, but we just make that basically about 1,000 times better. And then we do something else. We have these wonderful mirrors, all right, and these mirrors are some of the best mirrors in the world, and we suspend them on little glass fibers. And the reason we suspend them on little glass fibers is that provides the added level of isolation, about a factor of 1 billion in isolation. And so you put this all together and you model it, and it ends up working, actually, and that was remarkable for us. One of the things that you'll notice if you work in LIGO, you'll see a lot of people that are dressed up in these white suits, and that's for contamination. That this instrument is so sensitive that even a piece of dust that gets on a mirror causes a problem and can actually burn the mirror and cause the mirror to be damaged. So we wear these, we call them bunny suits. This is a place where cleanliness is truly next to godliness. Okay, so now let's talk about the first gravitational wave detections. The gravitational wave that we first discovered it in September of 2015, September 14th, 2015. And it was really right after we'd built our new version of our interferometer and just turned it on. And it just so happened that about 1.3 billion years ago, two black holes happened to orbit around each other and then collide and merge and produced a gravitational wave signal that started propagating outward. That had to propagate 1.3 billion years before it got to us. So we were very, very lucky. In fact, that when the signal was hitting the edge of the galaxy, we weren't a civilization yet. This was about 30,000 years ago. It came in eventually when it hit the Earth. It hit it on September 14th. So what did we actually see? So these are the waveforms. And these are now, at least in the field of gravitational waves, iconic. So if you go to the LIGO observatories, I see it at Caltech, I've seen it at other universities, you can buy T-shirts that have these waveforms on them. So we can actually make money selling gravitational wave T-shirts. I think that's pretty cool. What did they represent? It turns out there's a tremendous amount of information in these waves. And from analyzing the waves, you can extract that what we saw was basically two black holes. One was about 36 times the mass of the sun. The other was about a little less than 30 times the mass of the sun. And again, these are very compact objects. The bigger black hole was 210 kilometers in diameter. So, this is basically the size of a little bit bigger than metropolitan Chicago. For example. But that has, again, I want to stress the numbers here because they're kind of hard to get your head around. In that compact object, the masses were 36 times the mass of the sun. All right, so I'm going to play the movie, and this is actually not an artist's conception. This is actually a reconstruction of that gravitational wave data as the objects orbit around one another. And they collide, and they eventually form this big, massive black hole. So what you saw was the shadows of these black holes going around, but what you also saw was the stars in the background dancing around, and you actually see, let's go back here. Yeah, you actually see this sort of halo that goes around them. The reason you see that is that the gravitational field is changing so rapidly that the light that's coming from the stars behind it are actually bending around, and it's happening dynamically. And you also saw at the very end there was a burst of gravitational waves, all right? And that's what happened right as the two black holes collided and merged, right? Now, this event was remarkable in many respects. First of all, it was the first gravitational wave ever directly detected. It was the first observation of two black holes colliding with one another. It was the first observation. It's the first knowledge we have that black holes can form in pairs. That was something that wasn't even known before then. It was also a very energetic and violent event, right? At the last minute, when that burst of, the last second, fraction of a second, when that burst of gravitational waves came out, the final mass of this object was 62 solar masses, which means that 3 solar masses, all right, were converted instantaneously, effectively, within a fraction of a second, into gravitational waves, and energy was carrying away. So that's like taking 3 suns and making them go poof and turning them into gravitational wave energy. I mean, that's remarkably hard to sort of get your head around. And you can calculate the power radiated, and it turns out that the power that came out of this was brighter than the entire universe, all right? But it was brighter in the sense that these were gravitational waves. But if you were to add up all the power from all the light being generated from the entire universe, from all the stars and all the galaxies in the universe, it was about 20 times less than the amount of power radiated in this event. So this is a very energetic and violent event. All right, I said that these signals can be recorded and played back, and now I'm going to do that for you. All right, so this is, I'm going to basically play the time dynamic of the signal. You'll see the waveforms, but you also see these streaks, which we call them chirps. They're the frequency dependence, and here we go. So you heard that thump. All right, we played it 3 times. We didn't see 3 of these things. That thump is basically the recorded signal of the gravitational wave hitting the detector. So these massive black holes that produce huge amounts of power, 3 solar masses, ended up making this little thump in our detector. I think that sort of sets the scale here. Now I'm going to do something a little bit different. So you can actually hear the frequency content, and I'm going to artificially shift the frequency by 400 hertz and play it again. So you heard that whoop, whoop, whoop. That's the characteristic sound or characteristic signature of 2 objects merging together, 2 black holes merging together. So this was a remarkable discovery, and it actually became very popular. It hit popular culture. So these are just a few examples which I like about how the public reacted to this. So there was a cartoon in the New Yorker magazine. You can't read the caption, but I will. There are 2 birds, and one of the birds looks over. Was that you I heard, or was it 2 black holes colliding? All right. If you know the Big Bang Theory, you can actually see there's one T-shirt, there's another T-shirt. So Sheldon Cooper liked our discovery. You can buy, this is actually great, you can buy fashion wear. So this gentleman here is an Australian swimmer named McAvoy, Cameron McAvoy. After the discovery, he was competing in the world freestyle swimming event, and his cap actually has the gravitational waves on it. All right, he's a fan. You can go to a website, it's called Supernova, and you can buy gravitational wave fashion. Unfortunately, you can't see it there, but these patterns are made out of our gravitational waves. All right, so the dress is quite expensive. It's about $200, but I can tell you that I've seen a lot of these dresses by people who work in the by women who work in the gravitational wave community. But my favorite thing, actually the other one that's interesting is this, somebody was in New York City in March 2016, so about 2 months after our discovery, and sent me a photo text of this, and this was an ad that was in the New York City subway. Scientists have found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a walk-in closet. All right, I've never tried to find one. My favorite is this. This is a cartoon that was published actually the day after our discovery, which says how great cartoonists are, actually, that they react this quickly. This is a panel from a longer cartoon. It appeared in the Guardian newspaper, and I'll set it up for you. So these are scientists. This says, obviously we can't see these waves. The only way we know they are real is by using another extremely sensitive device which detects scientists having feelings of excitement. All right, so there's that device. And you see there's a person here. This is a gravitational wave discovery. All right, and there's a person here who's almost as excited because he or she is eating a cheese salad sandwich. All right. Now, my favorite part of this whole thing is this little editorial comment. Fun fact. Scientists' emotional reactions are also a fraction of the width of a proton. All right. I can assure you that anybody who was involved in this experiment does not believe that. We were quite emotional after this happened. So we've been running our detectors for our interferometers for a while, and we've now built up a menagerie, if you will, of black hole mergers. And this is actually at the end of our second science run, which ended in 2017. And the thing you should take away about these plots, so there are 2 kinds of black holes in this plot. There are the LIGO Virgo black holes, all right, the ones that were detected by gravitational waves, and those are the sort of the cyan bluish ones. And then there are, I'll call them EM black holes. These are the black holes that have been discovered in our galaxy using basically X-ray astronomy, because when black holes orbit around, or stars orbit around black holes, matter accretes and it produces X-rays. So the thing and this is the mass actually of those black holes. So there are several takeaway points here. First of all, We detect black holes that are much heavier in the sense that they're more massive. The other thing is that we are able to detect more of them. So this represents 2 years, effectively, of actually a little less than that, of integrated LIGO data. All right, whereas these guys right here, the EM X-ray detections, represents about 40 years of X-ray astronomy. So in 2 years, if you count them, you'll see that we've exceeded the number of detections that by 1 or 2 than the X-ray astronomers in just 2 years. So this tells you that this is really a new and fundamentally revolutionary tools for studying black holes. The other thing I'll tell you is that this is dated, that we are in the middle of our 3rd science run, and while we haven't actually claimed any what we would call true detections, we typically see an event about every week now. So we're up to on the order of 30 to 32 or 33 detections. And remember, in these detections, we actually we get 3 black holes. We get 2 that came together and gave their life to form that 3rd more massive black hole. So this is really enabling us to start asking and answering fundamental questions about how black holes form, in what environments they form, and as we get more data, we'll be able to even go further here. All right, so the other interesting part of this story happened in August of 2017. It's not just about black holes. Earlier in the talk, I showed you these 2 neutron stars, the example, the cartoon of or the artist's conception of the 2 neutron stars that were dancing around one another. Well, that is a very viable source because we know from other fields of astronomy, radio astronomy, that neutron stars can form in pairs. And black holes have a fundamental issue, all right, and that's that they're black, all right? They don't produce electromagnetic radiation. They don't produce light. We don't believe they produce light. So the only real way to study these kinds of mergers, the black hole mergers, is to actually use gravitational waves. Neutron stars are a different kind of object. So when 2 neutron stars collide, and I'll go into a little bit more about the physics of a neutron star in a second, they not only produce gravitational waves, they also produce light across the electromagnetic spectrum. They produce visible light. They produce radio. They produce X-rays and gamma rays. They even probably produce, we haven't definitively seen this yet, but they probably produce neutrinos, which are these ultralight particles that come out of nuclear reactions. And the reason they do that is because neutron stars are fundamentally different. Black holes are basically regions where space and time have gotten to a singularity, a point where there's an infinity. We don't even know what is inside the event horizon of a black hole. Neutron star is much more complex. Black holes are actually pretty simple from a physical standpoint. Neutron stars are much more complex. You can think of them as basically giant atomic nuclei. All right, so these objects that I said are very compact, 25 kilometers, about 1.5 solar masses, are made up almost entirely of neutrons, but they're 1.5 times the mass of the sun. So they're giant atomic nuclei. And when they collide, all right, it's a much more spectacular event because they produce all these kinds of different radiation. All right, so the trick, and this is the problem that you have when you're trying to do gravitational wave astronomy, is where is the source? All right, so if I have a telescope, all right, and the best telescopes can get things really, really precisely, I can point to a direction of the sky and I can say, oh, there's the Magellanic Cloud. I'll point my telescope and I'll see it. Or there's M87 and I'll see that. Gravitational wave detectors suffer from a big problem. They're not directional. They're in fact more like microphones than they are telescopes. So if I put an object in space like a star, I want it to produce a gravitational wave, maybe 2 stars colliding. All right, the only way I'm going to know that is if I have multiple detectors. And the idea, of course, is very simple. It's basically this idea of triangulation. If I can measure the time difference, the arrival time differences of the waves as they're hitting 3 different detectors, all right, in principle, I get a location. In fact, I get 2 locations, but for one of them is always going to be a preferential one. All right, so I need not only 1 detector, I need 2 detectors. So there's the 2 LIGO detectors that I talked about. And there's also a 3rd detector that we work with in Italy called Virgo. All right, it looks much the same. That's the picture in the upper left-hand corner. It looks much the same and is much the same as the LIGO detectors. So the Virgo detector started operating on August 1st of 2017, and soon thereafter, we saw something very interesting. But I should also tell you that there's more detectors coming, all right? Because the more detectors you have, the better this localization occurs. So there's one under construction, and actually it's just starting operation now, underground in Japan, and there's one that we're working on in India. So this forms a network, and we all work together, all right? And the reason we all work together is that this issue of localization is a real critical piece of doing multi-messenger astronomy. So how does it work? All right, so suppose there's a gravitational wave event. There's 2 neutron stars colliding. Happens some distance away and in some part of the sky. By basically resolving the time delays with these multiple detectors, all right, we can basically get the information. And if we can do that quickly, and by quickly here I mean in minutes, if we can within minutes identify where that source came from, we can tell our astronomy colleagues who operate telescopes that go point your telescope up there or wherever it came from, because that's where the gravitational wave signal is coming from. And this is very powerful because it enables this concept of what we call multi-messenger astronomy, using light, gravitational waves, and at one point neutrinos to be able to do this. Here is a really bad example, but it's a stark example of how hard this is. So this is an event that was recorded. I'm not sure it's the event ID, I'm not sure it's the date, but this was an event that was recorded in one of our, the current run that we're in. And those patches of the sky that are shaded, either in orange or light orange, show you the imprecision with which we sometimes measure these events. All right, so this is a particularly bad example. The area over which this object could possibly be in those contours is basically a quarter of the sky. So no astronomer, all right, is going to have the capacity, capability, or patience of trying to look over a quarter of the sky. First of all, because they don't have time, because when these neutron stars collide, things happen very, very rapidly. Virgo turns on August 1st. On August 17th, this is what happens. And I'm going to play another movie for you. This is basically the movie of some of the snapshots I've been showing you of neutron stars before. So let's play that movie. Did you hear that? Whoop. That was the recorded signal, the actual data of the recording of the gravitational wave recorded. In this case, I think it was in the Hanford Interferometer. Now, this movie goes on for a while, but I froze it there because I wanted to illustrate something. All right, when these 2 neutron stars collide, they produce lots of stuff. First of all, they produce a lot of matter because you have basically it's a giant atomic accelerator in space banging these 2 nuclei together. All right, they produce, first of all, something called a gamma ray, and that gamma ray shoots basically, if the orbit is in the plane like this, the gamma rays shoot out like this. And these are short, hard bursts. They last for a few seconds, that's it. And it turns out that while this event was being recorded in LIGO, and that's the signal, this is another one of these time frequency plots there. And this is a beautiful signal. I mean, anybody who's a gravitational wave physicist, gets, their mouths start opening and they start drooling when they see it. This is a plot. These other 3 plots are basically plots taken from 2 satellites, the Fermi satellite and the Inaugural satellite. So these are satellites that look for gamma rays. And you'll notice that you can't see the time scale here, but the difference between this bar here and this bar here is 1.7 seconds. So 1.7 seconds after we see a gravitational wave signal, we see a gamma ray, all right? And now, here's the really fun part. It turned out it happened in the same part of the sky. So there are lots of patches on this. The first patch is this big arc that's basically the Fermi and Inaugural satellite, Fermi alone, the two LIGO detectors alone, and then you see that this Virgo adds something here. So this little patch, that sort of light green patch there, is the sky area over which, with the data that we have from the gravitational wave detectors and using the data from Fermi, we can actually say, okay, that's where this source came from. That's not thousands of square degrees. That turns out to be about 30 square degrees. Well, that got astronomers really excited. We sent out an alert. This was a remarkably amazing thing. We sent out an alert, and astronomers started looking. It took us about 4 hours before our data went out. Astronomers were in Chile. This is really lucky. The Earth turns, which means that your telescope can go from darkness to light and lightness to dark. The Earth was in a position where in Chile there was about 2 hours before the sun was going to rise, at which point they would not be able to actually do any searches. But they were able to do these searches. And here's what they saw. We're going to zoom in here, and what you're going to see are galaxies. There's about 50 galaxies, maybe a little bit less in there, that are known to be in this patch of the sky that are pretty close. And they zoomed in, and they zoomed in, and they zoomed in, and they found this galaxy. And this galaxy is NGC 4993 is its name. It's not a well-known galaxy. It's about 130 million light years away. And this is a picture of the galaxy in its quiescent state. All right, this is the picture that was taken by, I can't remember which telescope because so many looked at them, all right, after this event. And that event in the circle there is basically the light that was emitted in the optical regime by the aftermath of the collision of these two neutron stars. So this is a remarkable occurrence. In fact, astronomers who I've talked to, colleagues tell me that they believe that this was one of the most intense observational campaigns in the history of astronomy. The only one that probably would rival it was the discovery of supernova 1987A. All right, so why is this interesting? All right, well, it turns out that there's a fundamental question about where elements come from that hasn't been answered. All right, so if you ask yourself, where does the gold in my ring, my wedding ring, come from, or the silver in my watch, or the oxygen that I breathe? The answer depends on nature, and it breaks down like this. And this represents a synopsis of, basically 60 or 70 years of knowledge. So there are, all right, the light elements are hydrogen and helium. They're produced in copious quantities during the Big Bang. Then you have the next level elements, and you see there's a lot of things in light blue and dark blue. They're produced in supernovas, all right? So when a supernova explodes, basically it has a lot of heavy elements in it up through iron. And that basically that explosion can produce a nuclear-rich environment that produces more of these elements. The problem comes when you get to these guys that are in orange and yellow here, and particularly the ones in yellow. All right, and no one had any good idea. Well, there were theories that speculated that they may be produced when two neutron stars collide. But it took this event and this one event, all right, in spectroscopy, basically looking at the light from that event, to actually confirm that most of the heavy elements, we call them the lanthanides, or a lot of them anyway, are produced in the collision of these two neutron stars. So chances are the ring on your finger or the gold chain around your neck, all right, was produced billions of years ago by the collision of two binary neutron stars. So that's quite amazing to me. So I'm going to conclude with the future. All right. So I've told you about gravitational waves that we detect here on Earth using these big, massive detectors. All right? But that's just the tip of the iceberg, or another way of saying it is that's just one part of the frequency spectrum. So our gravitational wave detectors detect waves that have very high frequencies and very short periods, milliseconds are the light periods, hundreds of hertz and kilohertz are the periods. But the gravitational wave spectrum is very rich. and it goes down to longer wavelengths. So if you go down a little bit further, you get to waves that have periods of minutes to hours. And those waves are very interesting because they can tell us something about supermassive black holes, something about the early universe. So a new generation of gravitational wave detectors is being designed and built. It's called LISA, Laser Interferometer Space Antenna. It will launch in 2034, and it will be able to look at these kinds of events. Going a little bit further, you can have much longer gravitational waves. Those are looked at by a different kind of technique called pulsar timing, which is fascinating in itself. And they look for really supermassive black holes like are in the center of our galaxy, colliding with one another. And then we can even go to gravitational waves that have the period of the age of the universe, all right, that basically have billions of years. And those gravitational waves are important because they tell us something about the Big Bang. The technology that's being used there is much different from what we use here, but it nevertheless is a good way to actually study the early universe. So all of these experiments, or all of these detectors, are actually operational with the exception of LISA, this one right here, but it will be operational soon. So this comes back to the theme of the revolution. So like when Galileo first turned his telescope to the sky, he was looking in the optical regime. We soon learned how to build telescopes that had bigger apertures to see deeper into the universe. Eventually, people figured out that radio signals could be received from the deep universe. That's the advent of radio astronomy, X-ray astronomy, infrared astronomy. Those all developed in the 20th century. So what we're seeing is sort of a parallel path of development, that over the next 20 or 30 years, you're really going to see these new kinds of gravitational wave astronomical detectors start to reveal more and more about our universe. And the really exciting one is witnessing the birth of the universe. So our understanding of cosmology, which is the study of basically the universe, right now is fairly mature in the sense that there's a good theory, and most of the data, in fact I would say all the data, agrees with that theory. And what you're looking at here is a map of something called the cosmic microwave background. This was produced by the Planck Observatory in 2018. And those color fluctuations represent tiny, tiny fluctuations in the 3-degree background radiation of the universe. So what does that all mean? When the universe got started, well, we don't really know how the universe got started, and this takes us out of the realm of physics and into the realm of metaphysics or something else. The Big Bang started with the universe as a singularity, all right? The universe, something, causes that singularity to explode, all right? And immediately, almost immediately, we start forming gravitational radiation, gravitational waves. Matter starts to form in that epoch. And then there's something called the inflationary period, which basically space and time itself just dramatically accelerate and inflate. Basically, it's like taking a balloon that's very, very tiny and blowing it up to huge, and that happens within a fraction of a second of the Big Bang. All right? A lot of other things are happening at that time, too. It turns out that this process is basically opaque to electromagnetic radiation. And it's not until about 400,000 years after the universe is basically formed, after the Big Bang, that you see this background radiation. All right, and what you're looking at is basically the picture of that background radiation. So this is a snapshot of what the universe looks like about 380,000 years after the Big Bang. Gravitational waves, because they don't interact with matter, all right, can see back a lot further. So if we could detect gravitational waves from the Big Bang, we'd be witnessing the birth of the universe. And I think that would be a really fantastic discovery because we'd see the universe in a way that nobody else can. So I want to thank you for your attention. I'm going to stop there, and I'm happy to take questions. All right, I'll point out, by the way, before the questions, that I represent a group of people that are about 1,300 in number. So these are basically the logos of all the institutions and universities that are involved in gravitational waves, and if you look very carefully, I think right there, you will see Andrews University. Andrews University has been a member, I think, since 2005, 2006. Yeah, so Professor Tiffany Summerscales is one of the members of the LIGO Scientific Collaboration here. So really all the work that I've described, I'm just representing a lot of very talented, hardworking scientists from all over the world. So. Yes, go ahead.
How energetic of an event can you detect with the current?
So it depends on how far away the event is. So when I think of energy, I think in terms of of fraction of solar masses. The binary neutron star event that I showed you, which wasn't that far away, it was 130 million light years away, was, I think we calculated, you have to actually take the data and calculate the conversion. I think it was 2% of the mass, solar mass, so, all right, but that was close. These big black holes, they are much more efficient radiators, and they can produce, many solar masses. I think our record is five solar masses have been converted now. So it depends really on the type of source and how far you are from the detector, the sources from the detector. So, anybody else? Okay.
Thank you. Are you bold to try to estimate the commonality of black hole pairs based on if you have one a week, and I assume the edge of your observational space is 5 or 6 billion light years, maybe, I don't know what.
Yeah, that's about right, actually. Yeah.
So then how common are these pairs? And do you dare to extrapolate from that how common black holes themselves are? Because there would be many that are singular.
Right. So the answer is that we're just, even though we've detected many of these things, on the order of 30 of these things, we still can't definitively tell you what the rate that we see these black holes are. And what we'd really like to do is measure that rate as a function of distance from us. So the more black holes we see, we're going to be running for another 6 months. My estimation, crude estimation, is that we'll see on the order of 100 of these types of events. So that gives you, I think, a first crack at what you're asking, which is over this volume of 6 billion years, converted into a volume, light years converted into a volume. So, we see 100 of these pairs. The really interesting part is, we only see these systems right at the end of their lifetime. So we know that for every one we see, there's some number, and that number is uncertain actually by factors of 10 or more, just because we don't exactly know the formation dynamics of these things. The other point to make is, you made a really interesting point. We see things in two of these. What does that tell us about isolated black holes? It's not so straightforward to infer, that you see, when you see two, that you're actually looking at the dynamics, because these two black holes have to form in a very special environment. They can either form from two supermassive neutron stars going through their stellar evolution, exploding, and when they explode, of course, they can produce energy that kicks the other black hole away. So it has to be, that orbit has to hold together. That's one way. There are other ways that have to do with dense stellar environments. So we don't even know yet which one of those scenarios is right. We have ideas, but so I would say it's early in the game to be able to sort of try inferring what we learned from the mergers from single black holes. But that was a good question. So.
No black hole neutron star pair.
Yeah, so I can only refer you to our public data. So our data, actually, I didn't put so there's more information here. We have a public database which basically records all of our events. And they're candidates. They're not actually certified as events yet. There is one candidate that looks very much like a neutron star black hole. Now, in full disclosure, I will tell you that I've been quoting these numbers in absolute precision. 1.3 billion light years, 36 solar masses. In fact, they're not that precise. The mass of those black holes is 36 plus or minus 4, all right? And the problem is the neutron star mass is pretty small. And because it's pretty small, the error bars sometimes leak into the black hole area. So we sort of can probabilistically say that we've seen something, but not definitively at this point. So, yeah. Yeah, I think it was actually quite well written. It was for distinctive contributions to the detection of gravitational waves. So the word there that caught everybody's attention were I think it was distinctive, things that clearly went beyond the thing. It's very interesting. I will tell you that I was fortunate enough to actually go to the ceremony, and I talked to the chair of the Nobel Committee, and actually one of the committee members. And the process of making a decision, they were very candid with me about this. I was very surprised. They said that it's never easy, especially when you've got so many people who've made so many big big contributions, how you pick among those. But this is, in the end, this is what they came up with. So, which I agree. I think I would have picked those 3 people too. So, all right.
So I've been asked to close with some appreciative thoughts. First of all, I'd like to express a lot of appreciation to Dr. Reitze for agreeing to come and give us this really great talk. I'd also, of course, like to express appreciation for the Kingmans who made this event possible, and future events as well. And so as far as a few announcements goes, students who are here who need co-curricular credit, there are sign-up sheets that you will see as you leave, so please look for those. For everybody who has come, there is a survey inside your program to give us suggestions for future Kingman speakers, so if you would take that survey, we would much appreciate it. And also, I wanted to let you know that since we are celebrating the very first of the Kingman Lecture Series, there is cake in the lobby, and please partake as you leave. Thank you.